Yeah, Dr. Farrah, we have conversations on the pseudo killers a lot about how vast the universe is, and we get a lot of questions like, well, how do y'all know? How do y'all know that the universe is such and such size and what's the age of it? So, could you explain what methods do we use to calculate the age?
Okay, anyway, hey, hi Ken, it's nice to meet you. And you just asked a very, very good and very difficult question. I will do my best with it. That I will try and avoid getting very technical here but I'll do my best. Okay, so let's take the age of the universe first. There are various ways to estimate the age of the universe, and the short answer to your question is we use all of them to try and work out how old the universe is. The first experiments to do this were done 100 plus years ago, and they didn't really have access to anything outside the Earth. There were telescopes. The first telescopes were invented, 300 and something, when was Galileo? 350 odd years ago. But they weren't terribly good. And so the first truly decent telescopes were about 100 years ago. So prior to that, we had to make do with what we had on Earth. And back then, there was still this question, how old is the universe? And scientists back then said, well, we can't measure the ages of other stars. And we can't now. I'll come back to that. But what we can do is find the oldest thing that we can on planet Earth, and then say the age of the universe is at least as old as this thing on Earth. Because if the Earth is this old, the universe has got to be at least that old. It's probably got to be quite a bit older. And the way that's done, and here I'm going to try and talk about something I don't really know much about, so that any of you might know more about this than me. So if I say something incorrect, please correct me. But my understanding of that is that what you do is you look for very old rocks, and then you use a technique called radiocarbon dating, where you measure how much of a certain type of carbon atom is in the rock. So a thing called an isotope. Right. And isotopes of an element are where it's the atom is basically the same, but you have one extra particle in the nucleus of that atom, which makes it a little bit heavier, but also makes it radioactive. And that radioactivity means it's going to eventually decay into its more normal counterpart. And so what you can do is you can look at that rock and you can say how much of the heavier isotope compared to the normal carbon is in that rock. And that ratio lets you estimate an age. And that's a pretty well-established method. It's been calibrated against other methods of age dating things. If my hazy memory serves, the oldest rocks that we have found on Earth are, would you believe, in Canada. And I think they're found in a place called Acasta. And I'm not going to try and pronounce the name of them. I think they're spelled Gneisses, which I think is Gneisses, something like that. Those rocks are age dated to about 4 billion years old. And so immediately you kind of know, well, okay, the Earth has got to be like 4.5 billion years old. Therefore, the universe has got to be older than that. Then the next thing that came along was a better understanding of how stars work. Because what you can do is, on a basic level, you can go outside during the day and you can look at our sun. Obviously, please don't look directly at the sun, but you can go outside and you can look at the sun and you can say, hey, you know what? The sun looks really similar now to what it looked like a week ago, a month ago, a year ago, 100 years ago. The sun has basically always looked the same. It's a stable object. And then you can go a step further with that, and you can say, well, the sun is providing all the heat and light we have. And so for life on Earth to have evolved, the sun needed to be pretty stable. Mm-hmm. And so you can then kind of immediately say, well, hang on, how old is the sun? And there are various ways of doing that. This is where, we would be here for hours if I were to explain the details of this. It gets a little technical, but it's actually, the concept of it is kind of straightforward. The way that the sun shines is by a process called thermonuclear fusion, where light elements fuse together to produce heavier elements, and that process releases quite a bit of energy. And so what happens inside the sun is you have a lot of hydrogen atoms are fusing together to form helium atoms, and that process gives out energy. So what you can do is you can look at the sun and you can estimate how heavy it is. And from that, you can get an idea of how much hydrogen is in it. And from that, you can say, okay, how long can the sun have been shining in the way that it has? So you sort of say, it needs this much hydrogen, there's this much hydrogen and helium now. Let's say it started off mostly hydrogen. How old must it be? You're kind of doing that kind of like, if you see it like this now, and it must have originally been like this, how long has it been around for to convert hydrogen to helium at that rate? And if you do that calculation, you get an age of about 4.5 billion years. But that's just for our sun. The next thing you do, I did tell you this was a very good, but very complicated question. The next thing you do is you say, well, okay, that's our sun, but there's lots of other stars. Like, the age of the universe has got to be at least as old as the oldest star we can find anywhere. And so what scientists did was they spent quite a bit of time working out how to measure the age of our sun. And then they thought, okay, well, that's great, but we can apply the same method to other stars, because you can see lots of stars in the sky. And so you can go to all those other stars and say, well, how old is this star? How old is this star? And if you do that, then you get this huge range in ages. The youngest stars that we can see are something like 1 million years old, which in astronomical terms, that star is a baby. Like, it's just been born. It's a screaming infant for all practical purposes. But the oldest stars that we have ever found are about 12.5 billion years old. And those stars are they tend to be, well, actually, they can vary in size quite a bit, but they tend to be quite dim. They tend to be not doing anything exciting. They're just sitting there steadily, gently glowing. But they are very old, 12.5 billion years. And so from that, you can immediately say, okay, the oldest star is 12.5 billion years old. The universe has got to be older than that, because you've got to have a universe before you have stars. The next thing, the last thing you can do, and this one gets a little weird, but this is actually ultimately the way we measure an age of the universe itself rather than an age of things in the universe. And that's to do the following. Back in 1930, different scientists all over the world realized that galaxies weren't staying still relative to each other. They're all moving apart from each other. It's a relationship called Hubble's law. And so if you look at a distant galaxy, that galaxy is by and large going to be moving away from our galaxy. And if you look at all the other galaxies, they're all doing that. And Hubble's law gets very, very mysterious and non-intuitive. We can come back to it if you guys want. But what you can do is you can say, okay, wait a minute, I can use this to measure an age, because what you can say is, if everything is moving away from everything else, then everything must have started out in the same place. And so what you can do is you can say, let's take the rate at which everything is moving away from everything else. And then you can kind of imagine that you are winding back that clock. And you can say, well, if everything's moving away, how long ago must everything have been together in the same place? And that gives you an age for the whole universe. And if you do that, you get an age of about 13.7 billion years.